Lesson 25, Simple Harmonic Motion, Springs. So we're going to be getting into something called Hooke's Law, which deals with springs. Um, to give you a bit of an overview here, if you think about it like, springs in your life, in the ballpoint pen, we have springs, like the springs in your car to keep like the road from being bumpy. We're also going to consider elastic bands springs, even though they're not springs. We kind of consider them springs in this case because they follow something called Hooke's Law. Okay, so here is Hooke's Law. And what it means is Fs, that's the force, the restoring force of the spring, is equal to negative Kx, where K stands for the spring constant, X stands for the distance. And what I mean by that, and here it is too, actually. So Fs is equal to negative Kx, along with, actually, I didn't show that on the last one too. Your period of a pendulum is over there too. You must have found that by now, though, hopefully. Okay, and if we look at Hooke's Law, this is what's happening. So you have an applied force down here, right? If I grab this spring, you can see the blue arrow there is the restoring force of the spring. That's what it's talking about. So in this Fs, that's talking about the blue arrow in this case, pulling back. X in this case is the green arrow, so it's the displacement this way. And the only reason that there's that negative sign there is because you can see that if I want the restoring force, it's always going to be in the opposite direction as the X value. No matter what I do here, they're always in opposite directions. So that's where that negative symbol comes from, right? Okay, here's the other part of it. You can see I've got spring constant down on the left here. So the spring constant, as it goes up, so now it's huge spring constant, right? Really stiff, big spring. If I grab this thing now, I have to put a lot of force, right? Like 100 newtons of force I need to apply to get 0.1 meters. If I put the spring constant down, now if I apply 100 newtons, I get a whole meter out of it. So that's really what the spring constant means. It's talking about the stiffness of the spring. So as it goes up, you can see it's even getting thicker, right? A thick spring would have a high spring constant. All right, so that's pretty much that. The other thing to notice here, though, too, is how it goes up. So if I make my applied force down to 0, right? If I apply a force of 1 Newton, you can see that the distance it was stretched was 0.01 meters, so like 1 centimeter. If I double my force, so I go up to 2 newtons, I doubled my distance, right? If I triple my force, I've tripled my distance. So they go up linearly. So if you were to graph this as force and displacement, or x, your position, it would go up linearly. It should go up like this. And your spring constant, K, if you had, let's say, a different spring, it would just go up steeper, right? But it does go up in a linear fashion like that. So that's the other thing to make sure you know about that. Okay, moving on. Okay, so these are pretty straightforward. So in a tire pressure gauge, the air in the tire pushes against the spring when the gauge is attached to the tire valve, as in the figure above. That's talking about this figure. So you can see that as you put pressure in here, it squashes this spring, and then you have some of the bar indicator sticks out more. Okay, if the spring constant is 320 newtons per meter and the bar indicator extends 2 centimeters, what force does the air in the tire apply to the spring? So we just really need our F is equal to Kx. And we don't really need the negative sign there. You could put it there. That's just going to show you the direction that's going to be involved too. But if we just want the magnitude of our force, it's going to be just drop the negative and you get 6.4 newtons. Number 2, when a 2.45 kilogram mass is vertically hung from a spring, the spring stretches by 12.4 centimeters. What is the spring constant? So in this case, the restoring force of that spring is going to be pulling back up again, right? It's going to be equal to the force of gravity. So if you drew a little free body diagram there, you can see Fg pulling down, Fs, the force of the spring pulling back up again, it's equal, just in opposite directions. So if you just figure out what Fg is by going 2.45 kilograms times 9.81, that's 24.03 newtons, then you can just rearrange our new spring constant equation and just solve by going spring force divided by your position. Okay, vibrating weighted springs. So now what we're going to do is, I'll show you. So again, I've cut the top off of some of the tools here, but you can, at the very top one, the only thing we're missing here is friction, so I can set the friction up and down. And then I've got some masses down here that I can hang from our springs, right? So if I hang this mass from this spring and then pull it, it's going to oscillate up and down like you'd probably imagine, right? Or if I like lift it up even higher, it's going to oscillate again up and down like that. If I had a different mass, it's going to oscillate different. And then I've got some just mystery masses over here. All right, so that's what we mean about like oscillating springs now, though. So this is simple harmonic motion, right? They have a consistent frequency and period, and there's always a restoring force back toward our relaxed position of the spring. Okay. Okay, so the equation for the period of a vibrating spring is going to be T is equal to 2 pi and then times the square root of m divided by k, where k is the spring constant. And this is an ideal spring equation. So this equation actually just assumes that our spring, it's kind of hard to watch, eh? I can't grab it. Okay, so I don't see a reset button, but if you pause it, you can grab those springs a little easier when you guys are doing it. So our equation is assuming, though, that these springs we're talking about are massless, so they don't have mass on their own. So that's like they're like totally weightless springs. So not really, but if you do have a if the mass you're using is quite a lot heavier than the spring, it's a good approximation. Okay, so example 3, just now using this new equation, right? Notice, though, that our new formula, notice what affects our period now. So the mass of the spring affects period, and our spring constant affects period. That's it. So in the last one, when we had the pendulum swinging back and forth, it was the length and it was gravity that affected it. So that's a need to know. You guys got to make sure that you know that what affects a spring system and what affects a pendulum system for period. Okay, so what is the period of a vibrating spring with a spring constant of 100 newtons per meter if a mass of 500 grams is hung from the spring? So there you go. Just plug the numbers in and see what you get for period. Okay, so I'm going to do the practice problems in this video, and then we are going to do a lab. Okay, number 1. A 500 gram mass is vertically hung from a spring. If the spring stretches 22.75 centimeters, what's the spring constant? So we got this thing hanging from a spring. We've got Fg is going to be equal to Fs pulling back up again. So really what I need is Fg. And then when I know Fs, I can figure out my spring constant easy enough. So Fg is equal to mass times gravity. So that's going to be equal to 0.5 kilograms, has to be in kilograms, times 9.81 meters per second squared. So that's going to be 4.905 newtons. Okay, so that's going to be what Fs is equal to as well. So Fs is also equal to 4.905 newtons. Okay, now our formula is Fs is equal to Kx. And it could be negative Kx if we wanted to know which direction we were doing, but we'll be all right if we just do this. So I'm going to say K is going to be equal to Fs over x. So K is going to be equal to 4.905 newtons divided by, now this needs to be in meters, right? So 0.2275 meters. So that would be K is equal to 21, and that should be 21.6 Newton per meter. All right, number 2. An ideal spring requires 16.5 seconds to vibrate 25 times when a 200-gram mass is attached to the spring. What is the spring constant? Does it matter if the spring vibrates horizontally or vertically? So we got to figure out what, when it tells us this, we can figure out our period quite easily, right? So let's figure out what that is first. So T is going to be total time over total number of vibrations. So that divided by 25. So period is going to be 0.66 seconds. Okay, now what we're going to do here is start off with our new formula for a vibrating spring. So that's going to be similar to the pendulum one, but as we saw up here, it's only going to depend on mass and spring constant. So M and K. And now it's asking, what is the spring constant? So we got to rearrange this thing. So I'm going to divide both sides by 2 pi. And I'm going to have T over 2 pi is equal to square root of M over K. I'm going to get rid of the square root by squaring both sides. And then squaring everything inside the brackets. And that's going to be equal to M over K. If you just rearrange this thing by, multiplying where you have to, or moving things diagonally, like I've said before, this was going to be K is equal to M times, I'm going to move 4 pi squared up to that side, and that's going to be over T squared. So K is going to be equal to, my mass was 200 grams, we deal with kilograms, so that's going to be 0.2 kilograms times 4 pi squared over, our period was 0.66 seconds, and that's squared. So K is equal to, it's going to be 18.1. Newton per meter. Yeah. Okay, now it says, does it matter if the spring vibrates horizontally or vertically? No, because all it depends on is the mass and the spring constant. It doesn't depend on G, right? It doesn't depend on like whether it's gravity is involved in this thing or not. That is only a factor when you're dealing with pendulums. Okay, so I'm going to get you guys to go ahead and do the hand-in assignment. I actually don't care which order you do it. We're going to do a hand-in assignment, like we've always done. And we're also going to do 2 activities here, so you can do them in either order. And I'll go through the activities, though, in the next lessons, or the next video. So that's it for that video.